So what are the patches and how does it depend on the material?
Well, so that's kind of a topic of speculation.
Yeah.
So one idea is that these are grain boundaries, and so you can model it as a grain has a voltage distributed over it, and its neighboring grain has a different voltage, and these for some reason fluctuate. So that's what we were hoping. And in future data, I'll show you that. I don't think I have it here, but the gallium arsenide point is like right there. So its heating rate is pretty high, and so that kind of, I wouldn't say that destroyed that theory, but there's something different about the gallium arsenide that maybe it isn't these grain boundaries. Other possibilities are that there's a surface oxide that gets charged up, and I'm not sure what mechanism that would be.
Surface states, no matter what.
Right.
Actually, the best material might be indium arsenide.
Why would that be?
Because of the band bending between the opposite direction and indium arsenide. So normally you get a depletion and then you have an insulated. So there's a doped gallium arsenide, but the electrons are not at the surface.
They tend to go
They are in the bulk of the material. There's a depletion. In the indium arsenide, the bending is the other way around.
But all the arsenides have a native oxide layer anyway.
If it turns out that it's an oxide, then
I don't know. The aluminum as an oxide, gallium arsenide actually people use it to protect it from oxidation.
I think if you keep it out of an oxygen
Probably.
reactor, obviously it won't have one, but I understand it's a very just a one layer,
Very
very thin native oxide. Do you think it could be something from the bulk?
No, from the surface. It's got to be surface.
but unrelated to the oxide, maybe.
No, when I say surface, surface is not limited to
Okay, so whatever the
a
surface.
monolayer.
What's the mechanical resistance of these bits?
So these, well, for this case, these are long needles, so their resonance, I guess we never calculated their resonance frequency, but the thickness of the needle is relatively thick, I guess, compared to its cantilever distance. That was more of a concern for the gallium arsenide. Okay, sorry, go ahead.
So these are fairly thick and quite tiny, so it's something else that
It's pretty low, yeah. So well below what the actual cellular frequency is.
and then what's called a megahertz, right?
Which is about a megahertz, yeah. Yeah, so these needles are 0.5 millimeter thick, and the distance from the needle tip to where it's supported is about probably 5 millimeters. For the third part of my talk, I'm going to discuss our shuttling experiments. And the reason that shuttling is important when you're considering building a large-scale trapped ion array is because you want to be able to move your quantum information around. And this is kind of an interesting thing in that in ion traps, this was, I think, looked at as a negative in that you have this large array and you have to be able to move your ions around. And that in other solid-state systems, this didn't occur because you would lay your solid-state system down and you would define the connections to its neighbors. But one of the nice things about this is that instead of having to move the quantum information around by swapping it with nearest neighbors and moving down the chain like one might have to do in a solid-state system, with ions you can shuttle your ion around to wherever you need it, to whatever region you need it. But in order to do that, you have to, for one, be able to shuttle along a line, but then also be able to shuttle through a junction, so that the ion can choose to go in either one direction or the other based on the voltages. So that motivated our research into building an actual junction and looking and trying to demonstrate this. We chose a 3-layer geometry for this, and this is one of our manually fabricated traps not actually have any trapping potential just because of the symmetry of it. But a 3-layer trap does, so that's why we built it. The fabrication of this was somewhat tricky. This is a really zoomed-in view of the T-trap, and this is its top ceramic layer with these gold wires on it. And the tricky part was that in this corner here, these wires are pretty thin, about 50 microns at its narrowest point. And so we couldn't just use a metal mask, physical mask, to lay these lines down. We actually had to do photolithography on that. Now, this is really not a conventional application for photolithography because photolithography typically deals with flat surfaces, but this has these really long, deep grooves in it. And so to get around that, what we did was we used the dry film photoresist. And so initially I tried doing this by applying the dry film photoresist to the alumina first, and then doing all the standard procedures. But the problem with that was that it left a residue that could not be cleaned off. And so to get around that, I spread a really thin layer of e-beam photoresist underneath, and then put the dry film photoresist on first, developed the dry film resist, dumped the trap in acetone, or squirted it with acetone for a really quick, short period of time to get rid of the e-beam photoresist that was under the exposed area, and then we put our metal down in these gaps. And that turned out to work in that we were able to make these really thin wires out here. This is sort of the finished product of this, zoomed in for a view of just the trap. You can see the trap structure is right here with all these static voltage lines going to the outside. So this wire right here contacts the middle layer, the middle ceramic layer, and goes out to the RF source. And then after these DC lines come out, they get connected via wire bonds out here. And those wire bonds then go to a grounding capacitor so that all of these DC electrodes are RF grounded. But then it also has a resistor in there in order to suppress noise that could be coming from outside, from these wires that are going out through the vacuum chamber. And so you can see all these wires here that had to be handcrafted and assembled. And that will be discussed a little bit later as far as downsides to manual fabrication of ion traps. In the junction region, we encountered a problem that turned out to be pretty formidable, and that is that if you consider a linear trap and you look along its axis, since the linear trap has segments with gaps that are much smaller than the length of the electrodes, it doesn't really have any RF trapping potentials along the axis. And so the ion can move smoothly from one end of the linear trap to the other. However, when you have a junction region, there does turn out to be an RF trapping potential that can be visualized as a kind of barrier here in this region. So in order to move the ion from right there, say, to over here, you have to give it a pretty big push so that it can go through this barrier right here. And so that was one of the persistent problems that we had in our shuttling routines, because we had to be able to tailor the voltages that were applied to these electrodes to push the ion into this region through the barrier, and then push it to the side before the ion would go up this side of the of the potential, and then squirt right back out. So that was that was accomplished through many simulations and processing Mathematica in order to determine the proper potentials to be applied.